Fisher left on the roll.
Probably seen a few things from me by now, coming your way, to teachers, to you individually. And this is the inaugural year for a program that the physics department has designed as part of an outreach program, a general outreach program. This one in particular, of course, is aimed at senior students who are particularly good in science, and we therefore call it an honors program. I would remark that part of the idea of this came from the fact that when I was a high school senior in Pittsburgh, Pennsylvania, it was something like this happened to me, and suddenly I was part of a program sponsored by Westinghouse, and they've run a program there for maybe 20 years or more called the Westinghouse Science Honors Institute, and therefore we stole most of the name. And they helped by providing some materials for us to get an idea of what to do. Now, their program is a little different than ours. It wasn't all physics, and of course, ours is going to be much better. So, in that sense, we'll be sending them information at the conclusion of the year. Now, it's also true that near Chicago there's programs like this, and there's no reason that a place with a physics department as fine as the one here at the University of Illinois should sponsor one, because we can reach pretty far, many communities around here. It turns out that in this first year, 23 schools signed up and more than 130 people. They're not all able to attend this particular session, as you can easily see here, but throughout the year we expect more people to come. And a little plug here, to our best of our knowledge, anyone here from Paxton, Buckley, Lotus, though they're signed up and they're involved in an important quarterfinal football game today, and we wish them luck. Accordingly, I brought a little football here just for you to think about things like there's a lot of physics just in football. There's a lot of physics in why you spiral in football, little ideas like that. So I won't tell you anything more about this one. Maybe I'll leave this as a puzzle for you to discuss maybe the next time. Why spiral in football? But what I thought I'd do before we go into the main program is perhaps each time I will have a little game for you. And in your folders, you should have these folders by now. Something like the second page of the folder, there's a little sheet there. And the little sheet says something that looks like you may have to fill it in. Okay? It has your name and your school and some lines there which are blank, and somewhere along the line it promises that I'm going to do some magic for you. So my suggestion is I will do a little physics magic trick, which has a completely reasonable physics explanation. Sometimes maybe I'll do one which is a complete cheat, and therefore you should call me on it. One of these times I'll do one that isn't physically allowed, but that's because I'll have something hidden. But this time they're reasonable. And what I suggest you do is scratch down your best answer to these two demos that I'll do, and drop it off in the wooden boxes on the way back, and we'll try to pick one or two winners or no winners or something for next time. So the first one, this one makes me a little bit nervous. It says dishes there, and you can see that there are some dishes down here, and it looks like I'm going to do something with the dishes, and I want you to think about what I'm going to do. Now, if I just knock them all on the floor, then you should write down, I told you so. But I'm going to try to pull the tablecloth out from under the dishes, and you can think about it as I do it. And actually, you should be careful when you do this trick, if you do this at home. And you have to get the right tablecloth, so you should go out and make sure you have the right tablecloth, because if it's made out of burlap, it may be less successful. Now, actually, it works better if you set the table properly, too. You should really light the candle and go for the whole 9 yards here. And pour some water, probably. But maybe you don't want to put a good meal on there. So watch. Sure, got the magnets in place? Okay. What happened there? I did this a little while back, and I quickly went over and blew the candle out, and I walked up to the transparency machine, and I started to talk, and someone from the back in the corner yelled, "How'd the candle go out?" They were taking notes. Okay, now that you're thinking about that one, I'll puzzle you with one more. And for this, I need a little background music. And I thought I would pick something that most of the kids today are listening to. Suppose you're thinking about buying your next stereo system. Working on speaker purchases. Let's start small. So I have a little speaker here, and I want you to listen to. I'm not going to say too much more. I'm going to do the demo, and I want you to think about what happens. You bought one of these speakers and you put it in the back of your car, kind of like this. It looks high-tech, okay? It's not a good idea. Suppose you just add one more low-tech piece of equipment to the system. This board here. Listen together. Oh. Why did it work?
And the flames went higher, and it burns.
Now it's like Jeopardy. This is music is Jeopardy.
You're like a child.
Well, let's go back to the main event here. Today, we're extremely pleased to begin the program, the Real Physics program for you. And the physics faculty here at the University of Illinois is about 70 people. And of those 70, we really took the time to try to select some of the things which are most topical and some of the best speakers that we could find. We're very, very lucky today to start the whole series off with Professor Enrico Gratton. He is the director and the principal investigator and the director of the Laboratory for Fluorescence Dynamics, which is located in this building. It's a very high-tech laser lab and biophysics laboratory. I think we'll just turn the program over to Professor Gratton, and I think that it's quite interesting for you to see that there's connections between physics and sort of the advances in biology today. So let's welcome Professor Gratton. He'll speak for a while, and then afterwards we'll take questions.
Okay, so I have to start this series on science here in this physics building. And I want to tell you a little bit about my work with lasers and how this work interfaces to whatever is going on in our society, mainly in the field of medicine, and how physicists can contribute in some way to progress in medicine. I have organized my talk with, first of all, some information about what really we are trying to do. Then I will do some demonstration with lasers and other funny things. And then finally, I want to show you some applications. And at the end, I will show you a piece of a movie to show you what science fiction, how science fiction is driving the way we do science and the way we apply lasers to different things. So first of all, I want to tell you a funny story, how I started in this field. And that was no more than 4 or 5 years ago. A famous doctor from University of Pennsylvania, Dr. Gratton, he has given really very, very substantial contribution to the field of medicine and physics. And he called me and says, Enrico, I need your help. I said, what? What really you need? And he said, I want to measure how long it takes a laser pulse to go through my head. He said, yes, I want to measure that. And I said, well, why you want to send the laser pulse through your head? I said, well, you know, I'm now 80 years old. It's really an old man. And I discovered now, at the age of 80 years, that if I shine a laser pulse through my head, it just goes through. It takes a little time to go through. And every time I do that on my graduate students, it takes a lot of time. So I'm very worried about what I have inside. At that point, I was really amazed. I said, you know, how come that you want to shine laser pulses through the head? What do you do? And I said, are you sure it's not dangerous? He said, no, it's not dangerous. You can do it. In fact, I will do some demonstration in a few minutes of that. So he came here the day after, you know, bringing his head. And he said, what is the laser? And then I asked again, are you sure you want to shine a laser pulse through your head? He said, yes, try it. So we sit him in front of the laser, to non-the laser. I say to my student, do very low power, you know, I want to blast his head. And then, to our great surprise, or at least to my great surprise, the laser pulse was going through his head, was not causing any damage. And that, to me, you know, was really a discovery in some way, although he knew that very well. And then we need to, at that point, to understand how really light goes through the body, and what we can learn by shining light through the body. In terms of physics, probably you are aware about that light is electromagnetic radiation, and that during, let's say, approximately the past 100 years, enormous progress has been done in the field, and we use electromagnetic radiation in many different parts of our activities. Every time you turn on a TV set or whatever, you are receiving electromagnetic radiation from some broadcasting antenna, and you have a receiver. In some way, let us say, in the last 100 years, we really learn, we understand how electromagnetic radiation goes through empty space, through vacuum, through air, and through many different objects. Instead, we know very little about how electromagnetic radiation goes to the body. We are, you know, let us say 100 years after the discoveries of the basic laws of electromagnetic radiation. But today, we understand very little. And in practice, for all practical purposes, we have here to go back to a very old idea by Newton, that we can treat light as particle. And you will see that whatever I will say today, I will consider light two made of very tiny particles, that they go through the body, like, you know, more or less a small particle will go through whatever. I will talk about diffusion of light, which is a very strange concept for a physicist. But today, we are 1993, this is the way we understand how light really goes to the body. And the progress that we made now is that we understand the modalities of how light is transported through tissues, and by really understanding the physics of the process, we are now already very important, I will say, progress in this understanding, and you will see how many applications today that are already there we can do, and how much we can do in medicine, not only from the point of view of seeing inside the body with light, but also in order to cure some diseases just by using light. And the field is really exploding. Probably by the time you will be 30 or 40, it might be that if you have some really serious sickness, like a tumor or whatever, you will go in a laser lab to cure rather than going to the surgeon that will cut a piece out of you. So let us see if we can start with some very simple demonstration. I have prepared here, I have a laser. Probably you are not accustomed to see this kind of laser. And actually, after the lecture, you want to come down and see what really is in the box, actually make it transparent in order that you can see it. And I have a laser which is tied to a very thin optical fiber. The optical fiber goes for several meters inside this box. And then ends up in a small hole. And you have a camera in this side, and you can see some, let us say, this hole you see in the camera. And if I turn on the laser a little bit, you can see light starting to go through. Okay. Now, first of all, I will do a very simple thing, which is to put my small finger in front and turn on the laser, and you can see that certainly light goes through my finger. And let me see if I can turn off the light. I will put my hand now in front, and I will turn on the laser a little bit more. And you can start to see now, through my hand, let us say the very light parts here are essentially the bones, and then you can see, let us say, some blood vessels through. And, it is clear that light goes through the hand, and be sure that I don't feel anything is totally non-invasive. Doesn't produce any harm, and everybody can try it. Don't just put your eye on the laser, but apart from that, as I say, harmless. And you can see very well some structures inside. And if you look here, I am not pointing to the fingers, those are the fingers. So I'm going really in the middle of the hand very well. So let me turn off now the laser. So you can see that the experiment that this doctor wanted to do in the lab is certainly feasible. This is a very low sensitivity camera. It's used, it's a very cheap $200 camera. If you have a very high sensitivity, you can really see the light going through the entire body. Now, here, that we can see very little detail of what is there. And that is really the crucial point in the use of light. The kind of experiment I have done was done, let us say, more than 100 years ago. People knew that light was going through the human body, at least thin part of the human body. Very little was known how you can illuminate the entire brain. But it is clear that light can go through. Now the point is, how come that you cannot see anything, or you see very little detail? Well, more or less you were able to see the veins and so on, but very little detail. What happens is the following thing. That light, as it goes through, it gets what we say scattered. It scatters on all the particles, the cells, whatever makes our body. And by scattering, in physical terms, we say we lose coherence. In such a way that when it gets in the other side, it's not possible to form an image in the optical sense anymore. So the image capability is lost, and we just get some sort of average intensity going through the hand or through other parts of the body. Now the reason for that is that there are many different ways the light can get to the other side. And those many different ways is that the light can either go directly through, or it can diffuse through the hand and get in the other side after a lot of time. So in some way, the light carries information of over all the path that has transversed in the hand or in the human body in general. And therefore, you will never be able to have a sharp image, because the light carries information, get absorbed, whatever, on a huge path. And this is due to the diffusive nature of the transport of light in the hand. Nevertheless, you can do a lot. And here comes the physics and the contribution that we give to the field. First of all, we can think about the light transport in the medium in a very different way. And that's the only part, let's say, I will try to convey some physics concept. And I will tell you that instead of using a light which is steady state light, we can use light which will on and off very rapidly. In that way, we generate waves of light. By generating wave of light, now we can measure, for example, how the wave propagates in the medium. And now, everybody will understand, I hope you have those concepts, that if you have a wave which is going through a medium, for example, when you drop a stone on a lake or whatever, you see that in the point where the stone hits the water, you have a wave going on, starting from that point. Now, I don't know if you ever try to have an obstacle. And what happens if you have an obstacle? It's simply that the wave gets a deformation. So it gets something like that. We say that the wave gets diffracted. Now, without going into the details of the physics, has been very clear for us that if we can study and we can measure the modalities in which the diffraction occurs, we can map the obstacles that the light encounters during the propagation in the medium. And this is really what we do. And I will show you some examples of application of that, and you will see how easy will be to see objects in a very highly non-transparent scattering medium, as we say, and nevertheless, just by seeing how the light can diffract the object, it's not really the light, it's that wave of light that is going to the object get diffracted, we can recognize the position of object. And of course, that would be crucial, very important, for example, in medicine, for recognizing where tumors are, where head injuries are. And I will show you several examples of that later on. So let me do another test, another example. I have here a beaker, which is empty now, and I will put some objects inside, no matter what they are. And then I will put a suspension, which looks like milk, but actually is a suspension called intralipid, which is actually used in a hospital for intravenous delivery. So it's a very, let us say, complicated stuff. It's not really milk, but has a very interesting property, is that the way it scatters light is very similar to our brain. So that will simulate more or less what is the brain. And of course, we are physicists, and first of all, we need to understand the really very basic physics concept. And I will put that inside, and you will see that the object simply will disappear. There is no, you will never tell that there is anything there. You can come close, no matter how careful you look. There is no way you can tell that there is something there. Well, I will show you some experiments that we did, that instead reveal the object immediately just by shining light with a laser, and seeing it's not really light, it's a wave of light, and seeing how the wave gets deformed by passing through the object. And by just seeing the deformation of the wave, we can realize where the objects are. So let me see if we can start with the slides. So this is the experiment. You see it's the beaker, exactly like the one we have. And we have an object that has a very definite shape. And we will illuminate the object from the upper part here. So light will come in this direction down. And then we have some sort of detector, a camera detector in the other side. And we are shining, as I say, a wave of light. And so first of all, we fill it up exactly like I did there. And there is no way you can see anything inside. But now let us measure the wave of light passing through. And this is what you see. So you see clearly the center of the object here. Those are the holders, those really very thin holders. And you can recognize immediately the existence of the object inside that small beaker. Now let's go back to the hand. Of course, this is a physics experiment. There is not so much we can learn other than, yes, we can do the experiment. But let us see the next experiment, which is the hand. This is a picture taken from an anatomy book. And this is essentially what you should be able to see. There are bones, there are veins, of course. And then I will show you an image done with that camera using waves propagation of this part of the hand. And I superimpose that image to an X-ray image that has been obtained, from an X-ray machine. And this is essentially what you see. So the background image is the X-ray image, and you can see very well the bones that has been enhanced in order to detect all the veins. So there is what we call a contrast agent that emphasizes the contribution of the blood vessels. And this is instead the image done with a laser, and you can see all the blood vessels more or less equally well. By the way, as a curiosity, this image has been used now, has become this kind of image has been used by the security industry I don't know if you have ever seen movies in which you put your hand in some sort of scanning instrument and then the door opens. Well, believe it or not, as a sub-product of this kind of research, the security industry is very much interested in using this kind of approach. And the reason is that every one of us has a different layout of the blood vessels. If you look at your hand and your knife or whatever, you will see that each one is different. And then the basic idea is that you put your hand and there is the camera that sees all the pattern of veins, and then will have a map in memory that tells you, yes, you are the right person or you are not. And it seems to be very, very difficult or almost impossible to counterfeit, let us say, the layout of the veins in your hand unless you really cut and add the one from another person. Okay, so in fact, it's unbelievable, but those kind of things that look like science fiction, so I say, instead are used for, in some applications in our industry. So let's go on. And okay, the next thing I want to see is that other interesting applications, for example, in dentistry, and this is a tooth, and you can see that you can detect, let us say, the shape of the tooth and cavities and so on inside teeth. And that is also a very interesting application. But as far as we are concerned, and for all the examples I have shown until now, we are really very limited of what we are doing. Because all the examples I have shown to you are so-called example of transillumination, so light that goes through one part. Now, the head, which we are very interested in studying, is really very thick. And for an adult, like Marian or whoever, I will show you some signals from his head later on, it's really very thick. And really, we get some light passing through, but it's very little. Instead, of course, for a hand, it's very thin, and a lot of light, was simple demonstration to show that you can see through. So the point is, can we do an entirely different approach and not only see light through one part to the other, but can we put through a source of light here and the detector there and see light from the detector, from the source going to the detector, when both are in the same side of the head? This is a very strange concept for people working in optics. And it's a very strange concept because light goes straight. This is the definition. We know that very well. Now I'm trying to prove to you that light in the body, in tissues, in scattering material, goes in circles. This is really, let us say, a relatively recent discovery, and makes up the possibility to do studies, even in subjects or whatever, in very thick tissues, like the head. And let us see how it works. Well, first of all, what we prepared in order to demonstrate that light goes in circles, of course, light in very highly scattering materials goes in circles, we start to study a material like something like this, it looks like milky substance, and then we pass through a fiber optic that illuminates with the laser in one point and the detector in another point. And then we devise a way, we're not going into detail, to see where the light passes through. And the point is the following. If all the light will go on the surface, well, there is not so much chance that we will ever be able to see into the brain. If you light just goes straight in the other side, there is not so much we can do because very little will go in the other side. It will not be nice if light comes down in the other and gets to the detector. Well, believe or not, this is really what happens. And this is me preparing for this kind of experiment. And you can see a very big tank where we can do very easy those experiments. And now you will see the pattern of the light. And let us see if I can describe you how this experiment, which is really a very crucial kind of experiment to demonstrate the utility of the method. So here we have the surface of the mirror that we cannot really study because it's essentially the detector will be in air. And in this point, we have a laser beam going into that sort of milkish solution, suspension. And then at this part, we have a detector. And what we want to say is, where does the light go that propagate from the source out to the detector? And you can clearly see that this experiment demonstrates that light goes in circles. And it comes out in the other side. So, although we illuminate in this point, we get the light coming out at a certain distance. Actually, I should say that the light that the detector in this position sees is only the light that goes in a very narrow circle. Now, if I make a section in this direction to see how narrow is the light, as we call light bundle, because it's made like a bundle of light going from the source to the detector, it's something like that. You see, this is the surface of the mirror. And you can see that essentially the section shows that light only goes in a very, very narrow path. There is nothing essentially at the surface, nothing in the bottom, and it really goes in an arc, very narrow arc, very well confined, close to the surface. And now we can do an experiment that in some way even the ancient people should have been able to do, to show that light goes in circles. And I invite you, when you get home, to do this kind of experiment. It's very easy, it's very revealing, and it works in the following way. You illuminate, you don't need really a laser. Let us say a flash lamp will do essentially the same thing. And just get a bowl of milk. Milk is as good as this very expensive substance here. And just look with your eyes at different positions on the surface of the mirror. And you will see that there is light coming out, let us say, from the surface. In fact, if I illuminate here, one point, there is light coming out from a large area. Now, the point is to demonstrate that the light that comes out from, is on the surface has very charge inside. And what you do is the following thing. Now, put a spoon inside the mirror, for example, in this position. And if what I say is true, you will intercept with the spoon all the light path going to the surface. And by interception of those light paths, you will see a shadow here, although the spoon is here. In order for the experiment to succeed at home, put the spoon very close to the surface and do the following thing. Move the spoon up and down in direction. And you will observe, you will be able to observe, that you will see a shadow of the spoon moving on the surface in this direction like that. This is really amazing, but this is what happens. And really do the experiment and you will see that a shadow of an object which is in this position is projected back on the same side of the surface. This is very, very basic, because that means that if we illuminate the head in one point, we can have an image of what is inside from looking at the same side of the surface. We don't need to go through. So whatever I will say in the next part of the lecture will just be a demonstration and application of this kind of light propagation in tissues. And this is really what we will expect. Now let us do the experiment, and those are experiments. Look also at the size that we are talking about. So we are talking penetration of whatever, 5-10 centimeters. And this is the shadow that we have at the surface. The experiment was done, we have a source and the detector, there is an object in the middle, so the source is here in some place, the object is inside, it's very important. Well, I cannot show it here in a 3D, I cannot really show how that's made, and this is the shadow seen by a camera on the surface. And those are, let us say, different ways to see also how the wavefront is deformed, but I will not go into any detail of that. Now, a very important thing, and a very, let us say, crucial point, is to show not only that light will go through milk like this one, a suspension, but it will also go through the skull and get into the brain. If light just stops at the skull, well, then we have no hope to see what is happening inside, isn't it? So we need to do another demonstration that light really goes through the skull. So we took a sheep skull, and empty, of course. We fill it up with the milky kind of suspension, and then we put an object inside the skull, and we illuminate from the outside. And the question is, can we see the shadow of that object on the surface of the skull? Although the object we know for sure that is inside because we put it inside. And here is the kind of shadow that you get. That's the deformation of the wavefront. And you can clearly see objects inside the skull, at least let us say, this kind of experiment. I will show in a few minutes real experiment on people. So here we have our smiling subject. This is Dr. David Friedman from Psychiatric Institute in New York. And this is not an image of Frankenstein movie, but those are our detectors. You can see those are really the light sources. So we will shine light, the light will go through an arc through his head, and then we will detect the light with a fiber optic detector. And then we want to see when the guy is doing some sort of activity, like moving hands or looking at images, how the light propagation through the head is changing. In this way, we can localize, that means the site where the activity occurs, how fast the activity occurs, and what is really happening. And that opens a new way to study the brain activity, to study psychology, and to see how really we behave, how we learn. For example, it will be very interesting to see if patterns of activity in the brain are related to learning. Might be in 50, 100 years, you will not do exams anymore, tests. You will just have one thing in your head, and just from the pattern of activity, we can detect if really you are getting the right answer or if you know how to do. And it really seems, for all the experiments that are available until now, that the kind of pattern of activity in the brain strongly depends on the level of understanding, the level in which you learn. At the beginning, the activity is very diffuse, it goes all over the brain, but then when you really grab a concept, you understand something, it seems to localize, to be very much in one single, all the activity comes out from one single point. It will be in some way possible to detect that, and maybe someday, I said, you will not do tests anymore, but just have some sort of helmet that will tell you to a professor how much you have grabbed of a concept. So this is the way we do the experiment. This is we need to, let us say, have a black stuff on the head. And this is in one of our subjects. This is Marion here sitting. And again, you can see the fibers, and the detector and the different sources. And now, let us see, we ask Marion, for example, to do some activities like move the hand rhythmically up and down. And we want to see if just by moving rhythmically the hand up and down, we can detect that activity looking into the brain directly. Or I think he also did some experiment just by moving, by tapping the foot. And of course we have to do that because if you look inside the brain, you have a lot of things going on. First of all, what do you believe we get into the, what sort of signal we have? Well, let us say this is a normal tracing. I don't know if that is your head or whatever, or you have never seen that before. But let us see what we get. This is, let us say, resting activity. There is nothing going on. There is no particular task be performed by the subject. And you can see that there is a very, very rhythmic signal going up and down, which is something you can recognize very well. You see the time it takes for an oscillation to occur is about exactly 1 second, and this is just the blood flow. Our brain is getting the blood, it goes with the heart rhythm, and clearly you can see that signal very well. So this is really what we have inside the brain, at least in the resting condition. Then there are other deformation of the signal you see once in a while, and those are related to the breathing. And in fact, if you count the number of seconds and you synchronize with the breathing, those are related to breathing. And that is clearly visible also from inside the head. And then you have very slow variation, very rhythmic, slow variation. And actually, that is, let us say, as far as I know, a recent discovery. It's not clear what that is, but this is in every subject, and there are some ideas. But clearly you get a very long-term variation. It takes about 20 seconds for the wave to form. We have no idea, what sort of things is that. Now, let us start and see what happens with the subject under exercise. And now you can see that, let us say, the whole pattern has changed very much. You can see many different ways, many different, we call frequencies there. So clearly the signal has changed. And now the question is how to unscramble that signal and getting out the information that we want. Again, a little piece of physics. And what we do, first of all, instead of graphing here, what is the detector activity, the detector as a function of time, we want only to see what frequencies, what sort of waves are in the signal. The reason why we do that is because we have the subject, we are asking the subject to tap, for example, every 0.8 seconds, and we have a timer, and we want to see in that tremendous number of waves activity, everything, if we can recognize the tapping signal, if it's there. So we do a trick that every physicist knows how to do, and to transform this signal, instead of displaying as a function of time, we just display what the frequencies of that signal are. And you can see here what the frequencies are. So first of all, you get the frequency, which is at 1 second, which is a very huge signal, which of course is the heartbeat. And those are what we call harmonics of the heartbeat. You see a little bit of the breathing. But then we do this experiment by moving the left hand. I think that is actually that's the experiment of foot. So we move the left foot, and then we look at the right part of the brain versus making the difference with the right part. So the left minus the right part. And you can clearly see now that the activity corresponding to the tapping, the frequency corresponding to the tapping, shows up very well here. And now you can plot how this activity changes as a function of time, telling the subject to tap at, for example, for 20 seconds, and then stop, and then for another 20 seconds, and then stop. And this is now a very clear graph of that activity. So there is nothing, essentially. And then it starts at 10 seconds the tapping, so the signal goes up, it stays up, and then we tell the subject to stop, more or less in this part, and you see the signal goes down and return to the level. And you have seen also how many other signals we have in the brain. We have, for example, there is a lot of activity here at low frequency. No, this brain is clearly having many other things going at the same time, and those are frequencies, rhythms, that we still need to understand, and they are really related to activities of the subject. So now, let's go to another kind of application of light going to tissue. This is a very recent one, that we have been working out more or less the last 6 months. And this is our subject, Cherry Johnson. She offered to do some exercise, and she had like a spring in the hand. And now what we want to do is to measure muscular activities. This is not brain anymore. And we want to say how the blood flows in the muscle, what is the rate the blood flows in the muscle. By doing that, we can tell if the muscle is in good health or not. If the muscle cannot use all the oxygen going through the blood, that means the muscle has some dystrophy, there is something sickness going on. If instead the muscle is able to use all the oxygen arriving, that means it's good. For example, that can be very important for athletes to see how much their muscle are trained to use all the oxygen. And so we build a detector here that we call an oxygen detector, because it detects in totally non-invasive way. We don't need to to inject any substance. We don't need to take any blood out, and we can see very well what is the oxygenation inside the muscle of this subject. And to give you an idea how the detector is made, we have now a series of sources. We need different colors. And there is like a little box which contains some lasers, electronics, and so on. And then what we do, we apply to an arm, and then we do several sort of a test in order to see how the level of oxygenation of the muscle is changing. This is a very important concept in medicine, to know how well tissue is oxygenated. I will show you later on about other example in which to know how tissues are oxygenated is of crucial importance. For example, you know that after surgery, many patients have a necessity to inhale to get oxygen. And that oxygen is simply because the brain and other tissues need a certain amount of oxygen. And probably you have seen in the hospital that there is like a gas valve, and you increase the amount of oxygen. Well, do you really know how much oxygen the patient is getting in? And if it's not getting in enough, do we have to increase it? And what happens if it doesn't get enough? Essentially, the brain gets damaged and the person will die eventually. So clearly, it's a very important thing. And up to date, the only way to do it is by drawing some blood, for example, every hour or every half an hour, and to check what is the oxygenation of the blood for that particular patient at that time. This apparatus allows us to do in continuous and non-invasively exactly the same monitoring. And it is applied to the arm, and then, for example, here we will do some exercise, and you simply follow on the screen the level of oxygenation during the different exercise, the different things. So you can see that essentially, you can have like a non-invasive, real-time monitor of what we call in this case the muscular activity. Another field in which oxygenation of tissue is of crucial importance, again, is for neonatal care. This is a unit built by a friend of mine, Mark Copy, here. He has been developing this unit in England, and this is from University Medical College in London. And what we do here in this picture we show, this is a premature baby. And one of the major problems with the premature babies is that the lungs are not developed enough to sustain breathing. And then the only possibility is to provide them with oxygen. And we need to know how much oxygen is provided. And if we provide too little oxygen, irreversible brain damage will occur, and the baby will eventually die or will be an adult with no capabilities. If we give too much, we cause also damage. And have to be just the right amount. And how you can tell what is the right amount? Well, for years, and only, let us say, in every place still in the United States, this kind of monitoring is not available yet. And what we do to the premature babies, we just provide some quantity of oxygen, and we hope that that is enough, and we hope that it's not too much. Instead, today, we have methods with lasers to optical monitor the head, to see inside the head. I said it's totally harmless, and to see how much oxygen we are really delivering. And then there is a system of feedback that will eventually open and close the valve in order to oxygenate the brain at the proper level necessary for that baby. So you can see here again, how everything works, and I will show you a little bit more in detail the fiber optics. Those are the fibers which are held in the head of the baby, and more or less you can see the size, and they are very, very flexible and very, very soft. Of course, you don't want to harm in any possible way, and the light goes in the center, and depending on the place where you apply the fiber, you use different size, and all the rest is black, essentially to avoid light from the room to get into the fiber. And you can see here much more in detail how things work. You can see the fibers on the head. They have been applied, so there is one and the other. And now you know that the light will go through an arc, will explore a part of the brain, and will tell us, essentially, for this particular experiment, of course there is not very much activity there, but will tell us, essentially, how much oxygen gets to the brain. And as I say, this is really crucial for the poor baby to survive. You see here the oxygen, which is delivered to the baby, and also, that looks more like a physics lab, you have seen that room, but it seems that the development of this instrument has become so important, and in the let's say medical community, they are really trying to get as many as they can, because it seems really to solve one of the major problems for premature babies, which is just to be sure that we don't damage them after they are born. You have here, that. Oh, sorry, I'm going back. Okay, so finally, I want to talk to you about another application of laser, which is the cure of diseases. Until now, we have seen more a monitoring, some sort of diagnostic, how we can detect what is inside, how we can detect the brain activity, how can we detect the oxygenation. But still, we have not really intervened in the subject, and we have not done any real action. Now, lasers are used very much for another process, which is called the photodynamic therapy. This is not science fiction. Photodynamic therapy is now used in several hospitals, in several places, and it works like that. Generally, it's used for some kind of tumors, which are relatively superficial, so are easy to illuminate, for example, for throat cancer. And what happens is that the patient is either injected, or is just shallow, some sort of drug that is specific for the tumor tissue. After about 1 or 2 hours that the drug has been injected, it concentrates very much in the tumor. Here is a diagram to indicate, that concentration. And then after it has been concentrated in the tissue, a laser light is shone on the surface. Of course, we don't make any hole, it's totally non-invasive. And the laser light has the property to initiate a chemical reaction, very similar to those chemical reactions that are used for etching electronic circuit, in which you have like a mask, and then you apply some light, and then you simply destroy some parts. It works in a very similar way. Now, since the drug is specific for the tumor part, which I indicate here in this way, also the destruction of the tissue caused by this photochemical reaction occurs only in the cancer, in the tumor part, in the cancerous tissues. And then that part gets almost, or let us say today, for many different kinds of tumor, get totally destroyed, and just the patient walk out of the hospital, doesn't need any, let us say, recovery, other than to be in the dark for some period of time, until the drug is totally metabolized. And it seems that at least for what I heard in the meetings, that for some kind of tumor, this kind of therapy is 100% efficiency, and you just get out, and that's it. So you get without a tumor. Of course, unfortunately, does not work for every kind of tumor. Now, I want to finish with some other slides to disappeared. Okay, about applications, and then I want to show you a piece of a movie from Star Trek, in which those applications, in some sort of science fiction way, really do occur, but really pay attention. That is, yes, of course, it's science fiction. Of course, we know that those things have been invented, but you will see how close they are to reality. So we see application to, for example, neonatal brain oxygenation. I have not have time to talk about a very important application, which is the detection of breast tumors. As you know, in the United States, one every 9 women will have breast cancer, and whatever, let's say 2 or 3 every 100 of those will eventually die. But still, it's a very, very substantial problem. So make an idea how many of you will get this kind of problem. So it's a very crucial problem, very important one, very important for women, very important for our society. And it seems that the early detection, when the tumor is very small, is really a very important point. If you can get it when it's very small, you can really get rid of it in a much easier way. There are really very substantial events in the field using those waves of light going through tissues in order to detect small granules, small abnormalities, and it seems to be a very promising thing. I didn't talk also about head injuries. Head injuries is a very also important problem in our society, in car accident or other sort of accident. If you get a head injury, really the most important thing is to understand as soon as possible if you have a head hemorrhage, and the only way to do now to cure is simply to open the scalp, and that's absolutely necessary because the pressure by the hemorrhage is such that it will destroy your brain and the tissue in that part, and then whoever will get this sort of trauma eventually will be unable to do some sort of activity or will be damaged forever. The point is that we have methods today, like X-rays and nuclear magnetic resonance or MRI, that tell you if you have it. The only problem that we have is that those methods work in a hospital, and the time it takes for a patient to get in the ambulance and get up to the hospital generally is too late. The brain has been already damaged. You need to have some sort of information at the site of the accident. This is why lasers, small portable units, can be very important in this field. And clearly, you can make a difference for the patient if you have a very early information about damage to the brain. We have seen an example of this in dentistry, muscular dystrophy, muscular effort in sport in medicine, applications to photodynamic therapy. I didn't talk at all about ophthalmology and surgery, in which also we have lasers in general have done very important contribution. I want really to see the 2 kinds of application, and I would like that you, in watching this movie, you will see this scene in which there is a guy that has a head injury and sits in a hospital room, and there is the 20th century, as they call doctors, ready to drill a hole in the brain, or whatever, in the head, in the scalp, in order to release the pressure. And then it comes the 23rd century doctor from Space Shuttle Enterprise, and they say, what are you doing? This is medieval, kind of medicine, and then he puts some sort of laser band on the head, and immediately he diagnoses what is wrong. You know, yes, it is science fiction, but I have shown you several examples of that, isn't it? And then just press a button or whatever, and then it cures. So he's done a very interesting photodynamic therapy. So let us look now with this kind of information to the movie.
What the hell is that? What are you doing? Dentistry? How do you explain swollen costs, respiratory rate, and common fungus? Most of his head's not the cancer. The artery must be repaired.
That's last year. This is that.
It's medievalism here.
See that?
Name, brand. Chekhov. Tank.
You have seen a demonstration of the 23rd century medicine. I hope it happened much earlier than that. Before ending, I want to mention my collaborators in this field. So those are the staff at the Laboratory for Fluorescence Dynamics here at the University of Illinois. And thank you very much for your attention.
Oh, great. I'm sure Professor Gratton will take some questions about the science fiction that he's discussed that's becoming reality. If anyone would like to ask, this is a great time.
Any kind of quiz.
Can you see tumors in the brain with this imaging system?
You talked about breast, seeing tumors in the breast and blood vessels in the hands. Can this be used in the midsection, like the heart or the kidneys, or is there too many, like,
This method still does not have the penetration of the X-ray method and MRI method. It's, let us say, more superficial. Although, you can go, let us say, 3-4 centimeters inside. So, more or less you can think about. In the case of, I don't know if you know how mammography happens, but mammography generally you require about 3-4 centimeters of penetration. That's the normal way mammography is done. So it is adequate for this kind of thing. The other thing is that for breast tumor, breast is very transparent. From the, let's say, physical point of view, it looks more like that mirror. It's really very transparent, so it's very easy to see through. In contrast to muscle, it has a lot of blood, so blood is red dark, so it's much more difficult to see through. Clearly, let us say that lasers in medicine can substitution for some of the primary methods like X-ray and MRI at all. I don't think in that way. But certainly, it's given a very good contribution and very good possibilities. So it's not really a substitution, but a complement.
Yes, I have a question.
When I look in, imagine that. Well, should we disclose the... No, okay, that's a normal question. No, we responded actually very well. Let us say, particularly easy to see through. Well, let us say the major thing that is unusual in the sense that people is unaware of that is a pattern of noise. Well, we call it noise simply because it's not rhythmic like the... And there is a noise, if you analyze in terms of, let us say, in the frequency, in terms of frequencies, you see that there are bands of noise. And those noises are characteristic of the brain, which means essentially that different parts of the brain, at least along the light path, like flickers in activity. And that flickers has some sort of, in physical terms, exponential decay. And so it seems to be uncorrelated activity. But this is the normal way. When instead the brain starts to act on something, that activity, at least as far as we know, is not random anymore and start to be coordinated. We don't know really what is happening. And very few people have any ideas of how the brain works. The brain work has been done, let us say, for many, many years using electrical signals. The problem with electrical signals is that you cannot localize where things happen. If you put electrodes in different parts of the head, it's very difficult to tell where the activity is taking place. Even if you have an electrode here and the activity is taking place there, you see, let us say, equally strong that it happens very close. So there is really no selectivity. So people have tried to do other things, and the major technique, let us say the one that has given probably the best result, is positron emission tomography, as you know, PET, as we call it. And the positron emission tomography, you have to inject a radioactive substance, and then by the decay of that radioactive substance and the localization, you can detect where that substance went, and then infer about brain activity. The time response of the PET, because you have to inject, you have to wait for about 5 minutes, is very slow. So so you can see only areas of activity, but you cannot tell what happens in terms of correlation of activity. You cannot tell is when that part of the brain light up, the other also light up after so many milliseconds. So you cannot get any correlation. You cannot really get a map, spatial temporal map of the brain activity. By MRI, people have tried only very recently, and it seems that you can see changes in oxygenation in different parts, although there is still quite a debate if what you are seeing is really brain activity or is just blood flow. But let us say that that is a very promising new method. And of course the optical methods that we start. Remember that the optical methods are, let us say, relatively easy to do. Well, Mario has been subject to that. You can hear that sort of helmet for, I would say, hours without, I hope, no major discomfort. MRI is a very different thing. So, again, it's, at this point in the game, clearly optical methods are very promising. Who knows, which method will provide better information specifically for the study of brain activity. Magnetic method, of course, also have been used, as you know.
About how long until this technology is used across the board?
Well, that's really a very interesting question. There are, let us say, two kinds of problems. There is, first of all, to understand what can be done. Second, there is regulations. And the United States is very strict about regulations. whatever, for the good or for the bad, that's a fact. It's very strict. And you cannot apply on people, let us say, for normal routine unless you get approval. The approval requires, in the United States, our legislation requires two things. First of all, that you don't do any harm, and that, of course, we agree about that. But also that it's effective. And sometimes, it takes years really to show that it's effective. In other countries, generally, the legislator is much more, let us say, open in the sense that it's enough that you show that you don't cause any harm. This is why some of the experiments I show were done in other countries. It's really a matter of legislation. And now they're trying to pass the same legislation also in the United States. I don't think it's a good thing. I think, to be more strict is okay. But I would say that it will take a lot of time. For example, I didn't talk at all about application to ophthalmology for curing, let us say, eyes for curvature and other things. There is nothing in the United States. Everything is done abroad because really we don't have any way to prove that the cure, which you can see immediately, will last for whatever, 10, 20 years. It's just impossible to show. How can you show that the light that you have shone in those infant heads will not do anything after 20 years? It's really impossible. The only thing, to get you an idea, I didn't talk that at all, how much light you get through. Well, I am now exposed to those light, and I get, let us say, some sort of 100 or 200 milliwatt of light in the surface of my head. The lasers that we are using, for example, were light-emitting diodes on Marian head, were less than a milliwatt. So a factor of 100 less than the light you will get on your head when you are just exposed under the tungsten. If you go in a sunny day, you get much more light through. It's only on that basis that we say this doesn't make any harm, because really we are talking about order of magnitude less than what you get in a normal sunny day. And we assume that to be in the sun, other than for UV that can harm your skin, let's say the warmth that comes from the sun is good. So.
How do you think your study?
Excuse me.
You mentioned legislation in what you just said. How do you think your study or the whole be affected by the Clinton?
I don't think it will. What we do is to study the principle. We are physicists. We are not doctors. Okay. So we develop the method, we develop the ideas, and then we build some prototypes. And up to that level, there is no problem. It's in the use in the medical community that needs approval. It's not for our, let us say, work. We don't need approval provided we show that our lasers are whatever class 3 or that they are not dangerous lasers. They have to be below a certain class, and of course they are. Otherwise, I wouldn't put my hand there for sure. Okay. So it would really zap the novas. The guy did. We use one of the big lasers I have in my lab. We use things that we know will not cause any harm. But there is really two different levels. One level is the research. You will understand maybe some data, and it's much easier to act at that level than to get something into the market. There are many other pressures, which is, it's convenient, it's cost-effective, it might be you develop a wonderful method, but it costs so much that simply it's not practical. So, we cannot act. When we do research, we do not act directly in that constraint. But certainly, to have, let's say, kind of inexpensive, compared to other medical apparatuses, instrumentation clearly will help very much. In fact, it helps very much in us to get funded and get money. As you know, if you read the newspaper, watch TV or whatever, clearly the problem of the expenses for our health is enormous, and we need to find ways to reduce it. So there is a big, big effort in, let's say, from the federal agencies to try to convince people to develop methods that will be really much cheaper of the one we have now. Although we will not do the same kind of thing, it will not be maybe so will not penetrate so much, but still will be very cheap.
Ask you if it had been, if the government had supported any of this, if they were getting interested, or if this is still just in the private sector.
No, the government supports very much. It's all, almost all the research in this field is made, because 90% is by grant funding coming from the federal agencies. The federal agencies have been very active. They solicit this kind of research. There are the big American companies like General Electric, Hewlett-Packard, Gratton, Dickinson, I don't know, let's say the big pharmaceutical company, all of have are in this field, in the laser, let's say what they call optical tomography. They have all programs in that, but still the major effort comes from federal agencies. So, and from the military, what's always true, the federal agencies.
Well, if there are no more questions, I think we should thank Professor Gratton again. Let me make a remark just before you exit here. The next meeting of our group will be January 22nd. Maybe we'll send you a reminder the week before if we get our little mailer working once again. Next time will be Professor Paul Goldbart, who's one of the young, very dynamic professors in this department. He'll talk about liquid crystals, so these little displays that you have in many devices these days, and some of the physics behind them will be kind of fun. One more remark, the little three-ring binders that we've provided for you, if you would remember to bring them back, we hope to bring little inserts each week. Perhaps it'll be something related to, like today, the laboratory for fluorescent dynamics. Next time it will probably be a photocopy of all of the slides that you can have and you can click through. Bring them back. And how about trying to bring your name tags back too? So stuff your name tags in the little pockets that you provided for next time. If there's anything that you have to suggest to us, just grab me or anyone else that looks like we're responsible, and you can tell us what suggestions you might have. Meanwhile, don't forget on your way out, drop off your explanations for our physics math. So long until next time. Thank you.